In this lesson, we will begin a discussion on the statics of particles. The content is from section 2.1 of the textbook. So our objectives for today are going to be to describe force as a vector quantity, examine vector operations that are useful in the analysis of forces, and determine the resultant of multiple forces acting on a particle. So let's begin with an introduction here about this chapter. So what we're going to do here is to focus on mechanics of particles. So the first thing to understand is, what is a particle? Well, a particle is an object whose size and shape does not have effect on the solution of problems involving forces. Okay. It's important to remember that this does not mean that the size of the object is going to be really small. Okay. So this whatever we learn here is not restricted to tiny or minuscule particles. In fact, if you think about examples of particles from the perspective of statics mechanics, we will see that an automobile can be treated as a particle. For example, when you think about its weight is acting at some point called the center of gravity of the automobile, and as far as its weight is concerned, the automobile is so small in the context of the size of Earth that you can think of it as a particle. Similarly, you can think of the Earth itself as a particle when you're thinking about describing its motion around the sun. So you can see here that a particle doesn't necessarily mean a small object. Okay? So we're going to develop two strategies here. One is a way to replace one or more forces by a resultant force that ends up having the same effect as the multiple forces. And the second is, we're going to derive a relation between forces acting on a particle so that we can find its state of equilibrium. So let's begin with the addition of planar forces. So first we need to understand about the nature of certain quantities we're going to deal with. So take a moment and compare the two lists of quantities below. We have on the first list we have forces, displacement, velocities, and accelerations. In the second list we have mass, volume, and temperature. So the question to you is, which list consists of quantities that require both a magnitude and a direction to fully describe them? Well, from your background in physics, you will realize that mass, volume, and temperature do not really have any role in terms of direction to be played in their description, right? On the other hand, forces, displacements, and velocities and accelerations, they all are based on direction as well as magnitude. So it turns out that these are quantities that are called vectors. So vectors are quantities that possess both magnitude and direction. And for the context of static mechanics, one of the most important laws of vectors is that they add and subtract according to the parallelogram law. So what is the parallelogram law? Well, if you think about this image right here, we have point A, and point A is being acted on by two vectors or forces P and Q here. You can then write down the resultant of this action of two forces as the resultant R, which is basically a new vector that can be found simply by constructing the parallelogram made up of P and Q. So what you do is you move P parallel to itself so that it aligns with the head of Q, and you move Q parallel to itself so that it aligns with the head of P, and thereby you've constructed the rectangle, or rather the parallelogram in this case, and the resultant is the diagonal, and that immediately gives you the net effect of having two vectors or two forces acting at point A. Okay. By the way, the other quantity that we mentioned here in the list, mass, volume, and temperature, they're called scalars, and they are quantities that do not possess magnitude, they do not possess direction but possess a magnitude. Okay, so here's another way to add or subtract vectors, and that is graphical. So let's say, you know, I have a graph paper and I describe the motion of an automobile or of a person, and I say that this person walks 9 units in the east direction, let's call it oriented with the x, and they walk some number of units along the y direction. So now tell me the vector that determines their final position. Well, vector addition can be done very straightforwardly by taking the fact that you have a vector having a tail and a head. Okay, so in order for addition to take place, what you do is you take the vectors and add them tail to head. So this is called the head to tail or tail to head method. And basically what you do is you take every next vector, every subsequent vector, the tail of that vector, and align it to the head of the previous vector. And then finally you join the resulting tail to tip, and you have your final vector. Okay? So this is called the graphical method. Now what we will be using more and more is a trigonometric method to solve for addition of vectors. And so just to remind you, first we want to understand what the notation here is. What this notation here shows are with an uppercase with an arrow on top of it, P with an arrow on top of it, Q with an arrow on top of it. These are indicative of vector quantities. Okay? So what this expression here is telling us is that the resultant R is the sum of the vectors P and Q, as we found from the parallelogram law. Now it turns out that there are also triangular and trigonometric ways to calculate the vectors or the resultant of vectors. And so the first one we're going to look at is something called the law of cosines. So if you look at figures A and B, so that's A and that's B right here, and you think about the two triangles we have here. So we have in blue is the resultant R, which is the sum of P plus Q, and it turns out that you can write down this resultant R, its magnitude given by this expression here. R square is the sum of the squares of the two vectors P and Q minus 2 times PQ with the inclusive angle between them, which in this case is B. Okay. Similarly, you can also use something known as the law of sines, and this one works when you have angles and the magnitudes of the different sides of the triangle, and this can be done by use of the equation here, where you take the ratio of the sine of an angle to the length of the opposite side. Okay? So for example, sine of A to the length of the opposite side, which is P here, I'm sorry, so this should be, oops, go back a little bit here. Yeah. So let's go back here and check this carefully. So this the sine law is with respect to figure A. Okay, so make a note of that, and I'm going to basically erase out these markings here just so that we are sure of what we're doing. Okay, so the law of sines, this one is written down with respect to figure A here. So as I said, it's the ratio of the sine of the angle to the opposite side. And so if I look at the first term here, it is sine of A, which is the angle A here, and the opposite side is vector Q. Similarly, sine of B divided by R, you can see sine of B, which is this angle here, and R is the opposite side. And likewise, the sine of C divided by the opposite side, which is P. Okay, so this is the sine law. Okay, so the parallelogram law along with the law of cosines and the law of sines, and if you want the geometrical method, these are 4 of the ways in which you can add and subtract vectors. 2 notes here. First one is something called commutation. So vector addition is commutative in that what that means is that it doesn't matter how you add the two vectors, whether you add it as P plus Q or Q plus P. And vector subtraction, you can think of it just like addition, but what you need to do there is to basically add P to a new vector called minus Q. So you reverse the direction of Q and you add it to P, and that gives you vector subtraction. Okay. Alright, now let's think about forces and resultants. Okay. So the first thing is to remind yourself about what a force is. It is the action of one body on another, and a force is characterized by the point where it is being applied, its magnitude, its line of action, and the direction in which it is being applied. Right? So for example, if you think about the case here where I have a particle at A and I'm applying a force on it along this dashed line, the magnitude of the force is giving us 10 pounds. Its line of action is this dotted line here, and its direction is 30 degrees from this horizontal axis. Right? So that gives you all the information about the force. Now it turns out that experimental evidence shows that the combined effect of two forces is basically a single resultant force. Right? Just like what we did for the vectors, the combined effect of two vectors acting at point A or particle A is the resultant vector R. You can now directly translate that idea and replace those vectors by forces, because it turns out that the force itself is a vector. Right? So it requires both direction and magnitude. So now in other words, this parallelogram law here can also be thought of as the parallelogram law of vector addition, or rather force addition, where the two forces P and Q are acting at point A. Now what about when you have several forces acting at the same point? This situation is known as having concurrent forces. So all the forces pass through the same point. And so for example, you can think of particle A here, and we have three forces S, P and Q all acting on it. And the question now is, what is the resultant? Well, in vector notation, the resultant is simply P plus Q plus S, right? And so you can find this resultant by doing the parallelogram sequentially. For example, you take P and Q, you find its resultant R1, and then you find a new parallelogram with R1 and the remaining vector S, and you find your resultant R. Right? So that's one way you can think about doing this. Another way you can think of doing this is to join the vectors head to tail like we did in the graphical approach, and that's shown here. So I take P, I move Q so that its tail meets the head of P, then I take S and I add it to the head of Q, and then I go from my original point P to the end of S, and that's my resultant R. Okay, so these are two methods, the parallelogram law and the graphical law. We're going to look at yet another method shortly, but before we get to that, let's think about something called components. So now what we just saw earlier was that you can take multiple forces and resolve them into one force. So that means you can also, by the law of commutation, take that one force and break it up into multiple forces. Right? So that's what we're thinking about here in terms of the force components. A single force can be broken up into multiple forces. The important thing to remember here is that the components that you have formed, the new components that you formed, the forces all eventually add up to give you the same effect on the particle as the original force did. So here are a couple of examples shown. So for example, I have force F shown here in red acting on particle A. I can break it up into P and Q shown by this small parallelogram here, but the challenge here is that you have multiple ways to break that force up. So you can see that you can have a different set of P's and Q's, so you have a completely different parallelogram, but the net result is the same. You have the original force F and yet another option here. So you have literally an infinite number of ways in which you can break up that original force into a pair of components that give you the same effect. Yeah. Usually in problems we will find that there are some simplifying ways to break up these forces, and typically what happens is that one of the components is known. So if one of the components is known along with the resultant, then you're basically limited in how you can choose the final unknown force, and this is either by forming the parallelogram or by constructing a triangle. The other case is when the line of action of each component is known. That means your angles are well defined, and so again you are now limited in how you can choose to find the force components of the original force. So typically in the problem you will have some additional piece of information that allows you to determine how to make these components. Okay, so let's take a pause here and work through an example problem, put all these things together. Okay, so here's the question. We have a bolt, and we have two forces acting on this bolt at point A, okay, right here. And the question asks us to determine the resultant, and what I would like to do is to show you how to use the SMART approach to solve this problem. Okay. So remember, the SMART approach is the S for strategy, which means what laws and principles should we use here. M is for modeling, means draw any figures to model the problem, include all information like the angles and the magnitude of the forces, and fill in any additional information you can. A is the analysis, where you write and solve any equations and crunch the numbers. And then finally, you reflect and think to see if your answer makes sense. Okay. So let's start with S. So one approach we could use here is the trigonometric solution. And that means that we want to create a triangle with the two forces. And so that means we need to move one to form, to make the head to tail approach. So we could either move Q and align its tail with P, or we could put P and align its tail with Q, right? And so then you redraw the vectors to form the triangle. And so in this case, I'm going to move P, and I'm going to align it with the head of B. So the two triangles, the two vectors are in red. And then my resultant is from the particle point A to the end of Q, which is R. And now you see here that I have also started filling in some additional information, like this angle here, which is 155 degrees, which is the angle ABC. So now if I pause and think, I have the magnitudes of these two arms, I have an included angle, and so by experience I can say, oh well, this looks like I can solve it now by the cosine law, and so I'm going to apply the law of cosines, because the only unknown in the law of cosines right now is the resultant R, and that's what we want to find. So I go ahead and solve, and you find that your resultant R value is 97.73 newtons. Right? And then you can reflect and think. For example, you can also go ahead and try to find this angle here. You can use a different approach if you want. You can use the graphical approach on a graph paper. You can use the parallelogram approach to see if that works. So for example, I'm going to create a parallelogram here and see if I can use that approach to find my resultant R. So if I look at this resultant R here, it looks kind of the same size and forming in the same direction as the one that I found here, which tends to suggest that our solution here may actually be correct. Okay. So anyway, verify this for yourself. Okay, so as a home exercise, try and solve this problem here, and again follow the SMART approach. So essentially you have a barge that is pulled by two tugboats, and what you're trying to do here is to find the tension in the cables or ropes 1 and 2. You should find that tension 1, T1 is 3,700 pounds, while tension 2 is 2,600 pounds. Okay, so with that, I'm going to end this first lesson. Please make sure to reread section 2.1 of the textbook and solve the exercise problem, and look out for any additional activities that will come to you via Canvas. Thank you.